our customers use our battery modeling capabilities to also gain a deeper understanding of their own system itself, especially with our physics-based models, because we're able to provide them more information than just the state of charge, the voltage, and temperature, a deeper understanding of what's going on inside the battery. They're able to optimize their system.
Welcome, everybody, to another exciting episode of the GT Tech Talk podcast. And today we have a very interesting topic on batteries. We have our hosts, me, Divya, and Ahmed. And with us today, we have Rebecca and Nikhil. Thank you for your time and for doing this podcast. Appreciate you being here. Maybe we can start off with quick introductions of what's your role at GT, a little bit background about you and the subject. Should we start with Rebecca?
Sure. Thank you guys for having us. So I'm Rebecca, and I am a software developer on the electrical systems team here at Gamma Technologies. So a little bit about my background. I got involved working on batteries when I was in grad school. So my master's thesis focused on modeling the coupled electrochemical volume change and stress generation behavior in advanced anode materials like silicon. And more specifically, we took an existing model and we reformulated it mathematically so that it could be solved faster than real time. So we took an implicit model, reformulated it into an explicit model so that it can be run on board vehicles.
That's really cool.
Thanks. I also feel really passionate about sustainability, and I found in grad school that I really took to applied mathematics really well, and I really enjoyed battery modeling and solving PDEs, and so that's what I do here at Gamma, and I really enjoy it.
That's nice. That's awesome. Thanks.
My name is Nikhil Biju. I'm a senior applications engineer at Gamma Technologies. I've been with Gamma for 2 years now. My background is in battery modeling. I went to University of Kansas for both undergrad and graduate school. Like Rebecca, I was also passionate about saving the world. And I remember taking this EV course during my graduate program. And when I was taking that course, I realized that batteries are the biggest bottleneck when it comes to any type of electrified system. And so that's when I kind of realized I wanted to focus on that problem, and just doing more research and work into it, I really got into battery modeling. And as an application engineer, I work closely with our customers to understand how they can use our battery modeling capabilities to design their products and provide services to their customers. And I work closely with the development side to understand what sort of features we need to develop in the upcoming versions, and of course, maintain the software, do a lot of testing and maintenance. It's a very exciting job.
Yeah, sounds exciting. Maybe we should rename this podcast as Saving the World One Battery at a Time or something like that.
I like
spin-off series.
Yeah.
Interesting. So we talked about what got you into battery modeling, and we talked about how battery modeling is a big thing. So it's gained the attention of a lot of people. So can you speak a little bit to the motivation behind battery modeling, especially in light of the push towards electrification in the transport sector, and then efficient energy storage? What's your thoughts?
Yeah, absolutely. I think you really hit the nail on the head. I think batteries have been brought to a lot of people's attention because of the drive, pun intended, to electrify the transportation sector. And what battery modeling does is it allows engineers to test designs of cells, of battery packs, battery modules with, less building and testing. which saves them a lot of time and money without having to make so many prototypes. I think another area for batteries too is the push towards clean energy just on like a global scale, right? Specifically like with grid energy. So as new clean energy harvesting technology develops, like wind energy and solar energy and then hydro energy, there's always going to be the issue of how do we store this energy that we've harnessed so that we can use it later. So
I think that makes a lot of sense. I think
Yeah, no, I think Rebecca summarized it really well. I think our customers use our battery modeling capabilities to also gain a deeper understanding of their own system itself, especially with our physics-based models. Because we're able to provide them more information than just the state of charge, the voltage, and temperature, a deeper understanding of what's going on inside the battery. They're able to optimize their system based on that more advanced information. But yeah, with anything, there's always challenges. And with battery modeling, one of the biggest challenges is the calibration process. So we could have a battery model that can capture everything in the system, but if that battery model isn't calibrated to the specific cell that you're working with, then it's not really useful, right?
Right.
So we spend a lot of our time to understand what kind of procedure or workflow we can design that customers can easily follow to have a calibrated model. And now the foundation of that is understanding what fundamental questions we can ask that can be answered by observable responses. So what I mean by that is, if we're trying to calibrate, how much capacity is inside each of the electrodes and how much capacity is moving back and forth, what observable data can we use to capture that, calibrate the parameters that relate to that? So for that, we use, very small discharge current known as the open circuit voltage, like the equilibrium voltage of the cell to calibrate those parameters. So we use that same kind of understanding to calibrate the rest of the parameters in the model and tune the model for the customer themselves.
That's very interesting. And both of you brought up a point that when we think of batteries now, everybody is familiar with electrification, but you also talked about storage and possibly other applications. Could you give examples of some of those and also see what kind of parameters that you talked about are important? I'm sure there are many, but if you could highlight a few, maybe we can help understand what different challenges different applications take.
Yeah, sure. I can start.
Yeah, go ahead.
So, there's different types of lithium-ion batteries out there. I won't get into the chemistry, but, high level, you have energy-dense cells, power-dense cells, and a balance of that. So the type of cell is used in a different type of application. So if you have a fully battery electric vehicle, right? No hybrid, no ICE, anything like that, then you need a battery that can sustain a large amount of current for a long amount of duration. So that's where you would have a energy dense cell. And then for a power dense cell, you might have a hybrid vehicle where you have these jolts of power that need to be required out of the pack or something like that. So, with this basic understanding, you can calibrate the particle size or the jelly roll thickness, stuff like this. And another big thing that we work on is aging. So with batteries, aging becomes a pretty big problem. And one of the biggest challenges we face is separating calendar aging and cycle aging. So what we mean by that is if you have your own like AA cell at home, if you don't use it for a while, if you just let it sit there at rest, it's gonna have like a different capacity after a set amount of time. So that same thing happens with the lithium-ion batteries, and that's known as calendar aging. So it's purely aging based on time, no current applied. And then cycle aging is when you have some type of like load being applied, and that's aging the cell. So in reality, it's the combination of the two that degrades the cell. So with our calibration procedure, we found a way to where we can separate the two mechanisms, identify the parameters that capture that specific mechanism, and then eventually you couple the two because now you've calibrated them separately. And again, that's all based on that initial approach of what fundamental questions can we ask to design a calibration procedure that will allow for that.
You want to add more to that?
Yeah, I think Nikhil did a great overview. I think I would just add to that battery performance varies a lot with respect to temperature. So there are a lot of parameters that we have to calibrate whose value changes depending on the temperature. And the way we model this is using an Arrhenius relation. So we have some additional parameters called activation energies for our diffusion related parameters and our rate constant related parameters that we have to calibrate as well.
And one thing that helps a lot with our calibration process is our material database. So we have a giant database of material properties for commonly used active materials for lithium-ion batteries. And that data was collected from performing over 1 million tests on coin cells, half-cell experiments. So we took that data and then put it into a database that users can use to see, if I were to change a cylindrical cell from LFP to NMC, what is the performance going to look like without really doing any type of calibration, just to see what would happen if you were to pick a different chemistry.
You elaborate the LFP and NMC.
Yeah, sorry.
It's not no, that's fine.
Yes, so LFP is a cathode active material. So that's lithium iron phosphate. And then NMC is also a cathode active material, but it's a nickel manganese cobalt oxide. And the anode material for these cells is typically graphite. We've seen commercial cells that are now using silicon inside, but there are pretty significant differences between the two. NMC has a higher energy density, and so that means you can pack a lot more capacity in a smaller amount of mass. And then LFP has a less energy capacity, but it is much more stable. So you're able to discharge the cell at a much higher C rate than NMC. And another thing that has been, pretty recently is NMC, I guess it uses pretty expensive metals, and the mining of some of those metals are also unethical in some parts of the world. And so there's been a great drive to use more LFP related chemistries, and recently we've also been having LMFP. So you just keep adding on letters.
All these acronyms.
Yeah. So, that's the motivation behind that chemistry, is to achieve a closer energy density to NMC, but still maintaining the advantages of having a much more stable chemistry and having a higher power density and stuff like that.
That's great, being conscious of the environment as well.
Yeah, that's the number one goal, right?
Yeah.
That's what we're doing.
So we touched on a couple different things like the materials database, the kind of different types of calibration and the aging models that we have in our software. And that's just a kind of a small snippet of all the things that we can do when it comes to battery modeling, right? And as I understand it, we have our standalone option for battery modeling, the AutoLion software. Can you speak a little bit about that? What kind of capabilities does it offer? What sets it apart besides the materials database, or even if it's just the materials database? I'd like to get your thoughts on it.
Yeah, we like to say we have multiple flavors of battery modeling. So we start from, if we're looking at making a decision between a battery model, there's a trade-off between computational cost and accuracy. And, that's again based on assumptions that you make for the model and stuff. So at the fundamental scale, we have battery, which it's known as their battery template. So this uses equivalent circuit. It's called the equivalent circuit model. And the idea here is you're using linear circuit parameters to capture physical phenomena. So it's really low in computational costs. It can be used in embedded systems, but it carries a low accuracy. And you don't get as much information about the cell as you would if you were to use a physics-based model. Going a level higher than that, we have something called AutoLion-RT, which is something that we've released pretty recently. And the idea there is that we're maintaining the same level of computational cost as the battery template, but it carries a higher accuracy and what we like to call a higher interpretability. And what we mean by that is you're able to get more information about what's going inside the cell because the parameters inside have a true physical meaning. And then, so those are, models that can be put into embedded systems, but we also have electrochemical models and physics-based models.
Yeah. So the next level up in complexity. So Nikhil kind of introduced our lower fidelity models, and I'm going to talk about kind of like the mid fidelity models that we have. So we have the AutoLion-1D template, which is the P2D or pseudo 2D model, also known as the Doyle, Fuller, and Newman model, which models lithium diffusion through the thickness direction of the electrode and also through the radius of the particle. So the way that model is discretized is at every location in the thickness of the electrode, we have an active material particle. And then one step further from above that is our AutoLion-3D, which is basically several AutoLion-1Ds in parallel. So it's kind of like the pseudo 3D model. So we have the diffusion in the thickness direction, the diffusion in this direction, as well as the diffusion through the radius of the particle. And both of these models are electrochemical models, so they are described by a coupled set of PDEs whose parameters have physical meaning. I also wanted to mention really quickly that the calibration for an electrochemical physics-based model is going to be slightly different than like an equivalent circuit model. So for an equivalent circuit model, its prediction and output is only valid over the range of data that you calibrated. So you cannot use equivalent circuit models to extrapolate or predict what will happen at conditions outside of your calibration range. But for an electrochemical model, because the equations and parameters describe the physical processes occurring within the cell, you can use those models to do some predictions outside of your calibration range.
And something recently that we've added into our collection of flavors is AutoLion-4D. We're just going to keep adding numbers to AutoLion. So AutoLion-4D truly captures 3D diffusion. So AutoLion-3D, you're not capturing the diffusion between different AutoLion-1Ds that are being solved in parallel. With AutoLion-4D, you're capturing all kinds of diffusion. So when we're thinking about the application side of things, what this allows you to do is be able to capture very intricate designs in the cell. So typically the anode surface area is much greater than the cathode surface area. And what happens is when those two electrodes are overlapped in the actual cell, there's a non-homogeneous distribution of concentration on the anode electrode. And in those overhang regions, you can get different types of side reactions that can occur from, greater SEI growth to lithium plating and so on. And so AutoLion-4D allows you to capture those types of mechanisms. In addition to that, you can also define your own side reactions that can occur. So if you have a specific type of film growth on the anode that you want to model, that's a reaction that you can add into our AutoLion-4D application.
Yeah, that's a lot of flavors, and you both
It is.
did a great job explaining. Are we having 5D, 6D in the future? Just
We
kidding.
want to get to 10 double.
Go battery team. One other thing was with these different flavors, do you perceive the same customer using different flavors at different for different use cases, or different customers use these different kinds of flavors? I hope that was not too confusing. What kind of customers use that, and what applications would they use it for? I guess that was my question.
Yeah, I think the best kind of application focused way to describe the different flavors is if we're talking about the V cycle, right? You start with some basic system requirements that you need to meet. So whether that's power requirement based on the peak torque your vehicle will experience, and then you use that to go all the way down into the detailed analysis. You're looking into your state distributions and thermal distributions, doing very physics based simulations, and then you work all the way back up and testing the design that you've come up with. So along that V cycle, you would use different types of models. So initially, you might just want to use the battery template to see, what are the power requirements for my battery? If this is the mass, these are the torques that my system is experiencing. And then when you get into more on the cell level and you're looking into what type of chemistry you want to use, that's when you can get into our electrochemical models. And then eventually work all the way back up again. So right now, a big part of our job is also to understand and develop a workflow to go from one template to the other and to go backwards. So we have had customers who use kind of all, not AutoLion-4D yet, just because that's a very new tool, but just going from, battery template to AutoLion-1D, or going from AutoLion-1D to AutoLion-3D to look at more of a temperature distribution on the surface of the cell or something. But yeah, it really depends on the customer.
As you probably know, machine learning and big data is kind of taking the world by storm. And we talked about how battery modeling could sometimes be the bottleneck in a big multiphysics simulation. So what kind of possibilities do you see that machine learning could provide battery modeling?
Yeah. So physics-informed machine learning is a very hot research topic right now. And as we had touched a little bit earlier with modeling, there's the trade-off between accuracy and efficiency. So with these really high fidelity physics-based models, you get a lot of accuracy, but with machine learning models, you get a lot of efficiency. So combining the two kind of gives the best of both worlds. And I'll give a specific example with hysteresis. So some battery materials, such as silicon, exhibit a lot of hysteresis between their charge and discharge behavior. And there's been some research and some papers published.
I don't mean to interrupt. Do you mind explaining what hysteresis is as it applies to batteries?
Oh, yeah, sure. So hysteresis basically means like a difference in the response of the material based on the direction of the input. So a discharge current would provide a different open circuit potential curve than a charge current. So if you're looking at a graph of the open circuit potential curve, which is just the voltage versus the state of charge, you would see two separate curves. They would not be on top of each other. And one way I've seen a physics-informed machine learning applied is using a machine learning algorithm to learn the hysteresis of a behavior and then have that integrated in with a physics-based model. And I think another area where machine learning will help is using data from a physics-based model to train your machine learning model, in addition to experimental data. So you can have that machine learning model apply over a larger range of inputs and operating conditions.
That would have a lot more real-world data into the picture too, that some things that physics-based simulations cannot predict. So you could kind of augmenting the whole thing.
Yeah, augmenting experimental data and simulation data with each other to kind of get a more like well-rounded, well-trained machine learning model.
That sounds really cool. I guess that gives me a good segue to ask my next question. We have worked with our customers to also build such models, and I think we have a really active customer base for batteries. So could you give some examples? We could also link some of these things so that the audience knows what you're talking about.
Yeah, I think so. One cool example that we worked on was being able to showcase how you can do a real world aging prediction for your specific system. So for that, we used some experimental data that we got from the Southwest Research Institute for a cell and calibrated an electrochemical model using our calibration procedure. And then we used that cell in a 1D vehicle model with a drive profile and weather pattern in Pune, India. And we simulated that for, I believe it was about 35 weeks. And we showcased how you can use this physics-based kind of interaction to gain more outputs than just the capacity fade. Understanding how much capacity you've lost to the film growth inside the anode electrode, and also answer higher level questions as, what is my 0 to 60 time after 35 weeks of cycling the cell.
So how much time did the machine learning model actually save you versus if you were to do the full?
Yeah, so we have had one application where our colleague Massimiliano, he's also an battery application engineer. He made a detailed electrochemical thermal model. This was a large battery pack module. And this was all created using AutoLion-1Ds and thermal finite elements for each of the cells. So running a simulation, using that big of an electrochemical model I think it took, some hours or so. But converting that using our machine learning capabilities, and the specific one that we used was a transient neural network that reduced that time to minutes. So it's a substantial improvement in terms of efficiency and computation costs.
And that was just on a regular PC. Right?
Yeah, it's on no supercomputers.
Impressive.
Really is.
We have also another fun application that we are involved in.
Yes.
And not to spoil too much, do you both want to add to that?
Yeah, one aside from me, discussing with our customers and industry, one thing that we also want to do is get back to our community and specifically academia and learning how simulation can help in terms of that. So one competition that we're excited to be a part of is called the Battery Workforce Challenge, where 12 schools around the country have a project where it's headline sponsored by Stellantis and Department of Energy and ran by the Argonne National Laboratory. And the idea is that each of these schools will be given a Stellantis vehicle, and they have to convert that vehicle into an electrical system, electrified powertrain. And so we are providing our simulation capabilities to 6 of the teams, where they would use our simulation to design their thermal management system for their battery pack. So we're really excited about this because we're getting to interact with students across the country, and actually not only just across the country, but we're also working with schools in Canada. We're also part of the competition. And someone who's purely doing battery modeling, seeing and working closely with students who are designing the whole battery pack, looking into the high voltage, low voltage system, looking into how do you configure a battery pack, actually do it instead of just typing in some numbers in the computer. I've learned a lot, and I'm looking forward to seeing how we can provide value to all those teams and to the competition.
It's especially nice in future work because you both started in college and you're here, so
That's
it could lead to careers of those students who are working on it. So it's pretty exciting.
exactly.
And we'll link to the website and feel free to check it out for more information. It's certainly really exciting.
Well, I think it's been a great podcast. We touched on a lot of different topics, and I'm sure as the battery modeling field advances, there's going to be a lot more to talk about and think about. So with that, I would like to thank our guests. Thank you, Rebecca. Thank you, Nicole. I would like to thank our audience for tuning in, and we'll see you next time.
Thanks for
Yeah,
having
thank
us.
you.